Now let's look at using finite differences and Matlab to compute approximate solutions u of xt to the heat partial differential equation du by dt is equal to 2 x derivatives of u to be solved on the domain x between 0 and 1 with boundary conditions that u is equal to 0 when x is 0 and that u is sine of 8t at x is equal to 1, and we'll specify some parabolic initial condition. Now in this module we're going to assume that integrating in task is a solved problem, and in particular we'll use the Matlab function ODE15s to integrate in time. So the only thing we're concerned with here is how to discretize in space. And the basic algorithm, the template for all we do subsequently, is algorithm 4.1 in the notes. Anyway, so you open up that algorithm and it's in the file heat.m in my system, and this is it here. And the first thing to do is to see that it does work, so we can run this by clicking on editor, run, and typically you then click on change folder, generates some numbers, and it plots this beautiful little graph over here. And this is a graph of u as a function of x and t. Running along here is space x from 0 to 1. You can see we started with a parabolic initial condition. And then running from right to left is time t from 0 to 0.2. And you can see as time t goes on, the solution smooths out to be almost straight in between the 0 boundary value at x is 0 and the sine 8t boundary value at x is equal to 1. So let's see how the function works. So the first thing is, so that the algorithm all fits into one file on the computer, is that we call the whole, we start out with function heat. The second thing is every document needs a title, and so we put a title as a second line. The percent character is of course a comment. Also every document needs an author and a date, so that goes into the third line. I've just put my initials here to save on typing, which is really cheating. Now the third line, somewhat frowned upon by professional computer scientists, but we'll use some global variables j and x, which we'll discuss later, and the reason for that is they are shared between functions. Then we define how many points there are in space. So here we're going to do 11, and then the next command on line 6 is to actually define the grid of points, the xj. So this linspace command, as you can see here, generates 11 equispaced points ranging from 0 to 1, namely 0.1, 0.0, 0.1, 0.2, 0.3, etc. Now out of all of those points, the two end ones are the endpoints where the boundary values are specified. We want to solve the differential equation at the interior points, and the interior points we index by j. So j is 2 to 10, and that indexes the x values 2 to 10 there, those 9 x values, and they're the interior ones. We now need to specify an initial condition, and here it is. It's a simple parabola, 6x times 1 minus x, and in this sort of formula, in this sort of context, we almost always use the dot times operator, because that does element by element operations. And you can see that in the result. Here is 6x times 1 minus x, starts at 0 when x is 0. By the time x is 1, it comes back down to 0 again. Okay, so then in the main function, the next thing that happens is we invoke ODE15s, and it has got 3 arguments. The first argument is a pointer to the function that computes time derivatives of the u at all of the grid points. Right, so we'll talk about that function in a minute, and it's a pointer because of that at character. The second argument is the interval in time that we want to integrate over. So here from time 0 to time 0.2. And then the last argument is the interior values of the field at the initial moment. Time is 0. Right. Now, what ODE15S does is it integrates in time and generates a grid of solution values u, and it returns the times at which it has computed something and the values of u. And you can see that in the solution over here. If you look in time, there's an uneven distribution of times at where there are values drawn on this mesh. And that's because ODE15S is adaptive. It determines which particular times it computes something at. The u values is a matrix of u in x and time. Now, to draw a nice plot like this, we need to put the boundary values of u in, because this u here is only the interior values, the ones that ODE15S integrates. So to do that, we'll put on either side of u, we'll put the leftmost boundary values at all the times t, and the right boundary value at all the times t. And that will form the larger array of the interior values, the left boundary value and the right boundary value. And it's that we plot with the surface command in the plot, and then label the axes so we know which is which. And that's all that the main function does. So now let's come down to some other functions. There's three of them. There's du by dt, there's the left boundary function and the right boundary function. So first, what's du by dt? Well, for ODE15S, it has to have this form, a function of t and a vector u, and it has to return the time derivatives du by dt. To do that, it needs to know what are the interior points j and what are the grid points x. So we put global jx so that we can get that information from the main function. Then we compute the spacing of the spatial grid. In principle, the spatial grid could have different spacing, but here the spacing is all the same, so we just take any one difference and that will do it. Okay, so then for computing the PDE, we want to know the leftmost value and the rightmost value. So for the given interior values from the argument of the function, we append the leftmost boundary value at time t and the rightmost boundary value at time t to make a larger u vector, one that includes not only the interior values but also the boundary values. Then the time derivative is straightforward to do. You just say ut for all the interior values j is just u of j minus 1, so that's u at the grid points just to the left, minus 2 times u at all the interior grid points, plus u times j plus 1, or u of j plus 1, so that's u at the grid points just to the right. That's our finite difference approximation to the second derivative once we divide by the spacing dx squared. Okay, that gets returned to ODE15S to integrate. Then the last thing is the left boundary condition. It's given by a function u left, and in this problem it's just zeros, so here we return a vector of zeros of the same size as t. So whenever, at the right boundary, the boundary condition is that u is sine of 8t, so there we just say return sine of 8 times t. And that's the function. It's the basic template we'll use. Now we can vary this a lot. The first thing to say is using 10 spatial intervals across the domain 0, 1 is not very accurate. So suppose we wanted to use more points, like 101 across the interval, so that the spacing in x is much smaller, and hence we think the approximation is more accurate. So we can change that and run it again. Let's have a look at the picture, and you can see the mesh in x is now a lot finer, and it's a lot smoother graph, and it still looks much the same as it did, but it is quantitatively a lot more accurate. And we can play with this a lot more, and we will do so in some further examples.